Okay, we are recording. All right. Okay, so we're going to continue our discussion of just ideas for training. Okay, so as I said in the previous video, we started with random tensors and just doing operations on them. Then we've seen a few machine learning algorithms, regression, particular, and then logistic regression, neural nets, and deep neural nets. We've gone as far as looking at a very advanced algorithm, which is PhD, right? And that shows a lot of the techniques and operations required to implement such a complex algorithm. So now we're looking at a set of problems that have to do with, okay, we had tensors with random weights in them. Now we want to look at how those random weights become, guys, how those random weights and those tensors actually become valuable, important weights, right? So that's kind of the idea. So we have to compare usually these metrics. And today I'm just focusing on regression type things, MSE, but also just some curve fitting, interesting ideas, right? And the goal is to minimize them. Today I won't cover cross entropy, but at some point we'll cover that for classification. So let's take a look over here at the next example. So the next, we're going to go to the GitHub. Okay, guys, shh, can you please be quiet? All right, so we're going to look at the next example in the same repo, and it's going to be normalize the losses, right? So we did curve similarity. So I had several metrics, and all of them maybe were telling me a little bit about those curves, right? So I'm kind of to, I have a curve like this, and I calculate several metrics, and they gave me different values. Maybe they give me different information. What if they give me different information? Could I combine the losses? I'm not saying you should or you shouldn't. I'm just going to show you kind of what you can do sometimes with losses, including the fact that you can include regularization parameters, all kinds of things, usually a distance metric of some kind, right? And this is the example I'm using just to kind of illustrate the idea, all right, of how to make a crazy looking objective function. All right, so I'm going to continue with this problem, but I'm going to create a new Jupyter notebook. And it's going to be normalized losses as kind of the title of it. And so we're just going to explore. This will help us to understand a few concepts additional in machine learning. And I'm going to try to justify why you would use them or not. So it may or may not make sense. All right, so I'm going to go back here. I'm going to create a new one. All right, I'm going to hit new, Python 3. I'm trying to keep these separate as different problems. So I'm going to add my cells. I'm going to rename this one, and I'm going to call it normalize losses. So I've mentioned many times, and the curves, I'm going to say the curves. Many times, I've mentioned that normalizing is really important in deep learning, and you do it all the time. You do it between layers. You do it for the input that goes into your model. You do it at the batch level. And these are a whole bunch of concepts that I kind of want to discuss that may seem complicated sometimes. So you'll hear something like batch normalization or batch stochastic gradient descent. And ooh, that sounds very sophisticated, right? And all these ideas. So I think this problem could help us to visualize this. All right, so let's go. But again, I'm starting from this same idea of the curves. Okay, so let's go ahead and do that. All right, so I'm going to need some libraries. I'm going to remove scientific notation so I can actually look at the data. So I'm just going to use NumPy for this one. Okay. And I'm going to go here. So in this case, I'm going to do, this should say 10. Oh yeah, I don't know why I saw this as 30. It says that. All right, so this 10 just means the batches, okay? So obviously in machine learning, you're going to have a batch. So that's, batch normalization. What does that mean? It means that we're loading a batch of data. We did this with the GPT, right? If you remember, we had like 32 or something. It just means 32 sentences, if you will, that were randomly selected and we're feeding them. And they're really independent unless we do some kind of a batch thing, okay? So in this case, just so everything is readable, I'm going to limit it to the size 10. And I'm going to create my curves. So if you remember from the previous example, I plotted this one, right? And that was basically one of a batch, right? But I want a batch of 10, so I'm going to create these kind of randomly, but just to kind of illustrate the example. So I have 1, 2, 3, 4, 5, 6, 7 metrics, right? That I had in that library. I'm going to go ahead. And I'm going to create just, NumPy array of zeros initially. It's going to have 10 rows, so it's a batch of 10. And actually 6, I'm only going to do 6 metrics out of the 7, okay? I'm going to call it curve sims. And it's initialized, and it's a 10 by 6, in this case, a batch of 10 by 6. Not the batch of the data, like in the GPT, but you can see where I'm going with this. It's almost like a batch of losses that I would have, right? Because I have 10 things that I'm running, training or testing, and then I'm actually calculating distances, 6 different distances between the two curves, the real and the predicted, and what do I do with them as far as the optimization objective, right? So that's kind of what we're discussing here. And this is, this is hard in machine learning, right? So, but all the time they're inventing new things. Recently, they invented DPO, like within the last 3 years. For GPT models, that's a loss objective. That's clever, very, very amazing, actually. So, this is an area of research. This is just an example in my case. All right, so I have my NumPy array here. So now I'm just going to populate it with random data. So I really thought about this, actually. Because I wanted to have different ranges in here, right? Different ranges. So if you look, I'm just going to, this probably could be better as a tensor operation, but I did a for loop for I in range n. So there's 10. And every 10, I'm going to just randomly initialize these values, and they will represent the metrics, okay? So there's like the area between the curves, the MSE, and so on. Do you guys get the idea? So imagine I'm training. My model predicted something. I have the real, and I calculate the MSE. Boom, I have that value. Then the real, the predicted, and I calculate the area between the two curves. Boom, I have that value. Then the Fretchel one, real predicted, get that value. And you guys saw from the previous example that they were in different scales, 12, 0.8, 20, and so on. But you did see that when they were far apart, the values were much higher. When I made them close to each other, the values were much lower. So obviously, there's information there. Do you guys see that? That is the crucial thing in deep learning. You see, I've decoupled the weights, right? So there's nothing of weights here, but different weights would give the curve that was far apart from the real one. And another set of curves, a more optimal set of curves, would give, two curves that are closer to each other. And you can actually quantify that with the metrics. And that's kind of my whole point. All right, so here then, I usually like to not read data sets. I like to run everything like randomly, and so it just makes it more succinct. So here I've already done the curve sims. So it's populated now, so I can go ahead and take a look at it. All right, so I'm just printing all the rows, all the columns, so it should be 10 by 6. And, it doesn't look, I wanted it to look a little bit nicer. I can format it a little bit better, I'm sure, but it's noticeable, right? So this is the first row. You can see the values are 26, 64, 120, 57. I think that's a 0.6 and a 768 and a really large scale. Notice the scale, 0.6 versus 768. Do you guys see the difference? But they are all after the model predicted and you compare it to the real, there's some metric, okay? Some metric of which one of these is MSE, as you guys know. All right, so I have my thing there. So now what would I want to do? At the end of the day, you could consider these as losses, right? So we'll see this a little later, but your loss would be MSE, spread. It'll be nn.mse, right? But I'm just going to assume I've instantiated that, and it would be spread, comma, real. Whoops. And this is usually what we do, right? This is what we have done, I think, in the first example that we did of regression, right? But what I'm saying is this MSE is actually just, I think it's just, let's say the last one, or let's say this one. So that's just one of 6. But obviously, these values are going down as the curves get closer, and that's actually what we want. So how do we use them in a loss? So that's the question, right? So that my basic, all these functions, by the way, are going to have pred and real, okay? So I'm just going to take it out to kind of ignore it, but assume it's there, right? So then now I have that, but I also have area, which is, let's say, this second one in every one of the rows in the batch of 10. And then I have Fretchel, but I also have PCM. Do you guys see that? And so obviously this would be the simplest thing to do. Will it work? You gotta try it. But do you guys see my point? So when you do loss backward, which is kind of like the next set of Jupiters, what do we do, right? So that's where we take the derivatives and then we take a step to update the weights based on the information. What is this information is what is in loss. And what is loss? Well, basically this, right? So that's the magic of a model working. So you guys, by default, most people for regression will just do that. If it's a classification problem, you do cross entropy and so on. But in this case, I'm kind of illustrating several ideas. And it's going to, so actually then, curve sim, so to be more exact here, it would be curve sims 0, right? Plus curve sims 1 plus ... plus curve sims, what is it, 5? Do you guys see that? So there's several questions here that you have to ask yourself. First of all, we have 10 by 6, not 1 by 6. So what do we do there? Do you see what I'm saying? Like, we have 6 things that we gave the model, and the model did predictions for them. And it gave us, for the first one, these 6 metrics. For the second one, these 6 metrics. So how do we use that information in the loss function? What do you guys think?
Maybe the straightforward approach is just taking a mean.
A mean, right? A mean of what? Of the batch.
Yeah.
Or a batch mean. Do you guys see that? Or the scales are different, so we normalize it. Where do we normalize it? In the batch. So it's a batch normalization. So it doesn't have all the information in the world, but if it's a batch of 64, statistically, that could be good, you know? So these are the things that you have to try out experimentally. Does that make sense? So yeah, exactly. So that's what I'm going to do as an illustration of those concepts, right? I don't know for sure that you have to do it. So I would try actually normalizing, not normalizing, although some things you do have to do, okay? So anyway, so this is the idea so that at the end you can get these losses that would be in your model, and then loss backward can actually do its PyTorch thing to update the weights, etc., based on the feedback from these losses. Does that make sense? Got it? All right, so I don't need this part. This was just for illustration. So the next step in the Jupyter, after we printed this, is to think about this idea here. So do that. So this is a normalization. There's two types of normalization. There's standardization and normalization. So there's the one that you calculate the mean and the standard deviation, and your values end up between like -2 and +2, standardization. And then there's the normalization, which is where the values end up between 0 and 1. Okay, so I believe in the past I've done standardization examples. So in this example, I'm doing normalization. It also kind of is more intuitive in terms of losses, okay? But I'm also going to do the means. So there's a lot of ways that you can do this. This is a straightforward one. You take curve sims and you use NumPy's linear algebra.norm, and basically that helps you out to calculate this. So now I'm going to, not sure why I did 5 there. All right, so I'm going to run this and I'm going to print it. And if you notice, whereas before I had values in the scale of 26 to 236, other values in the scale, you know, like 768 to 1200. Some values are like 9. You know what I mean? They're different scales. So that's what the data looked like before. And now if you notice, they're all should be between 0 and 1, I would say. Do you guys see that? Does that make sense as a concept of normalizing the data? Remember, you can do this for anything. Like you actually can do it for your input x's. Just keep in mind, I'm doing it for the losses here as an interesting exercise. Notice a couple of things. You could argue that you want maybe these values to add up to 1. Because I was adding them. Remember, I was doing loss equal 1 and the other. So if I take, so this is MSE, this is mean absolute error, this is Fretchel, this is PCM, this is area between two curves. So if I wanted to add them, 0.51, 0.53, that's already over 1. So 1.3, 1.38. Remember, we have talked about this idea called a softmax, which we've never maybe seen in action independently, but you've seen it in your algorithms. So in this example, I could use softmax to make all these values add up to 1 for some reason. So we can consider that. Also, I need actually the mean of the batch, right? I can't just give the whole batch to the model, right? The model just needs a metric. So the loss is really just the value. We've printed it many times when we've done this exercise, right? It was like 0.8, 0.6, 0.4, you know, it's going down. So we need to do that. So that should be the next step. So how do we do that? We just take the mean, basically. So in this case, I'm going to do NP mean of norm matrix 2 on axis 0. And then hopefully I'm going to end up with a 1/6 instead of a 10/6. So across the columns, it's just going to take the mean. This is something that is done extensively in machine learning. If you think about it, you have these batches of 64. You can't really mean across all the data because it's massive, right? When you're but why not just across the batch? That may give you some important information, batch normalization, batch meaning. So here I'm going to go ahead and run it, and you can see it is now 1/6, which means I have taken the means of the losses and then maybe use this information now in my actual backward calculation. Any questions, guys? Yeah, go ahead.
I mean, in this case, we are normalizing the values with respect to each other only.
Yes, only to the batch. Yes.
Yes, but the features are with, like, we're meaning across the column. So all of those features, like the MSE, it's only going to be mean across the normalized across the MSE. My point is that, for example, if we have a very small absolute error, like 0.001 for one thing, and a very small mean absolute error, if we normalize it, it actually increases. And
does it really?
Yes.
Okay.
I mean, do we want that or no?
I don't know. I'm not saying that you should. You have to try that. So this is just an example of normalizing and so that they would be sort of on the same scale. Because you could argue that one. I'm not even saying that you should do this, because it might be that one can stay at 250 and one can stay at 20 and they still go down. You know what I mean? So that can happen. Remember, this is different. These are losses that I'm talking about. Now, as far as your point of not the mean, but the normalization, you said?
Yes.
So very small values.
Yeah. Will they not get normalized scale between 0 to 1, like you said?
Well, that should be what they do. So do we have an example of that to look at it?
Yeah, we have like really small values and things here, but
sure. So I could do for this one 0.0003, might be smaller, right?
Yeah, and maybe remove 26 because it's 26 plus.
Oh, is it? Okay, yeah. Just do 0.26. Or yeah, let's remove it actually. All right. So like that, right? They're very small, the first ones. Okay. And then the normalization issue.
Yes, at least that's my understanding.
No, it's fine. Like, yeah, you know. So let's normalize. So this is just an example of normalizing to put things in the same scale. So these all became higher. Point. So they're all relative.
Yes.
My answer is the thing that we did in that metric, right? They were all changed. They're all relative.
Yeah.
They're actually, the reason why I'm saying normalizing them is just so that maybe one doesn't have way more influence than another one.
Yes, but when we are decreasing the loss, for example, NAE decreases, but then we normalize them, then it gives the signal to the model that, hey, it's not actually decreasing.
I think I understand your question, but we haven't yet like taken a step to decrease it. This is just, we take the real and the predicted, take the difference, and we're going to do that consistently every time. So think of it like this. Let's take this value, 0.11, right? So in the first iteration, this comes out as 0.11. The weights didn't do anything. Next time, 0.11, didn't do anything. Then something happens to the weights that was really good that did decrease it. So I think as long as they decrease consistently, unless this is going up now instead of...
No, I mean, even if the losses increase before the normalization, because we normalize after, so the losses decrease, and ideally or expectedly it should decrease for all the batches or all the samples in each batch. And then we normalize.
But I think the goal is still for it to go down. Like the values, even though this was 0.008, the difference, and now it is 0.11, it's still better that we have not 0.11 but 0.8, right? Still the goal is to minimize it. See my point? Because then the model should do that. All you're saying is like a multiplication, but they're still proportionately 0.0003 and 0.0004. This one is better. And when that converts to 0.11 and this one is 0.10, this one is better, right? The lower one. So then it doesn't matter. Because maybe the scale gets like out of whack or something. but the values consistently become a thing that you still want to minimize.
Sure.
As long as that's still the case, I don't see a problem. It would be like if like it's 1 and then it's 1, oh, you know, like 3 and then 1/3, like they're going in different directions or something, but they're not, right? If I understand correctly. So that's what question I'm asking you. Like
I mean,
0.003 is 0.002 better? Yes. So 0.0003
but
becomes
when it
0.11.
normalizes, increases. My point is, for example,
Yeah.
if we have losses at the start to be 1,000,
Mm-hmm.
they will still normalize to a value between 0 to 1. And if we have later on losses 0.001, which should be good, but again, they normalize to 1. The thing is, it sends a signal to the model that, hey, it's doing nothing.
1 over. And make that become the loss. So if it's going in one direction, just make it the other direction then.
Then we have to change something.
I mean, if you're saying that, I think what you're saying is that, you know, if we have 0.003, what we want is for it to be 0.001, right? So go down. So if the equivalent of that, I don't know that like I would have to do the multiplication, but if the equivalent is 0.11, and if the goal is still that it should be 0.10, and that's better, then I don't see the problem.
But can we say for sure, like it will go down? The normalized loss will go down? Can we say for sure?
Well, okay, so this is 0.003, 4 zeros and a 3. And then the other one is 0.4 zeros and a 6, right?
Yeah.
After we did the thing, which one is it? The second one. 0.059. Okay, and the next one, 0.11. So 0.003 was lower, then 0.000 is higher. Yeah. And then we would want then lower higher. But at 0.059, right?
Yeah, this is also lower.
Lower higher.
Each other.
Yeah, so there's lower higher, right?
With respect to each other.
Yeah. So I think it's fine. So 3, 6, lower higher. 0, 6, 11, lower higher. Yeah. So then they retained. I mean, the scaling is like maybe it was better the other way. I don't know, but my intuition is we're still trying to minimize it.
Right.
Yeah. And so the only thing, as I said, I don't read too much into this. I was only trying to show you that losses can be made up of more than one thing. I mean, it's a very common thing. You have a loss plus a regularization parameter, or a loss and a distance. In this case, the easiest thing for me was to have 6 metrics and add them together. But then there's issues of scale. So which one is better? Experimentally go ahead and try it out. Okay. I can't print all the losses and see what's happening. Could be that one loss takes it up when another one takes it down. So this is hard stuff. People do their PhD things and then ultimately they do some weird loss function, right? So that's kind of how it is. All right. Yeah, so hopefully that makes sense. Good discussion. All right. I did the normalization as an example. And then I did the means. So then now, whenever you think of a batch, it's just a convenience thing. You have a batch of 64. Hey, convert it into you have 64 by 6, make it 1 by 6, and boom, you have data that is actually actionable, right? And you can use that in your model training. Got it, guys? All right, so one last thing that I have in here is softmax. I'm not saying you have to use softmax, but I kind of threw it in there because it sort of made sense. So what do I mean by that? So let's take a look. So here I have values 0.27. So do these values add up to 1? They may. So let's do some of them. So sum of means. Okay, let's go ahead and run that. All right, it does not add up to 1. It is actually 1.7. This is not so related, I would say, to losses. This is definitely related to classification, where we have 0, 0, 1, right? And we want the probabilities to match that. So make, 0, 0, 1 adds up to 1. 1, 0, 0 adds up to 1. 0, 1, 0 adds up to 1. So we might want to add that, but I kind of threw that in here to illustrate that idea. So what is the softmax basically? It's just, it'll take a vector like this one, where it does not add up to 1, and it'll modify the values just a little bit, and now they will add up to 1. So we'll take a look at that. So I created my own softmax, by the way, instead of using the PyTorch softmax. So you can look at the formula there. Uses exponentials, basically. Okay. And we talked about softmax a little bit in the GPT last week. You guys saw that was also used in the GPT. So I'm going to hit run here. Just added the function, basically. I encourage you to play with it and take a look at the outputs. And then now, basically, we are going to run our vector just like that, which is, this one, which does not add up to 1. And now we run it. I called it A. And now I do sum of A. And it does indeed add up to 1. Got it? So this is, for some reason, maybe you would want to do this, although here it doesn't apply so much to this problem. Got it, guys? Are there any questions? So here we discussed some of the concepts of batch normalization, batch means, and basically the idea of adding the losses, okay? And remember that the goal of these things is usually to minimize everything to 0. So kind of the intuition might be with this vector. So actually we can go back to this vector over here. You might, the weights in a perfect world, which is rarely the case, right? In a perfect world, we get to the limit of how much the Fretchel, optimizes. So you might get stuck at 0.23. But it could be that this one, the area under the curves, 0.31, still, you can try different weights that still improve it, right? And key is that this is not changing. So it kind of arrives as a stability point, and then this one starts to go down, and then the loss may go down. But as I said, these are things that depend on the problem, and they're difficult to implement. All right, that concludes this Jupyter, this example on normalizing batches, etc. Are there any questions before we move on to the exciting world of calculus? Any questions? Or we'll do a very simple example. All right, so everything that I've been saying so far has been metrics that we use to kind of get the difference between curves so that one curve ends up on top of the other curve, right? We arrived at the point where I have created these losses vector, this vector of losses, and then I just started adding them together, right? So I have loss, and let's just say A plus, well, I'll say PCM metric, but also my MSE, right? And mean absolute error, MAE, right? And the Huber, MSE, and then Fretchel, area under the curves, etc. Many of these, right? So we are using them to create a loss. This is an object in Torch. And so that's what we're going to kind of study right now. And this takes us to the computational graph, which is a pretty complex thing in PyTorch. So at the end of the day, so keeping it simple now, just the idea of MSE. So we're just going to focus on MSE. We have a loss, and that loss is going to be Z minus T square, right? So, oops, sorry. Right, guys, you agree that that's kind of MSE, mean squared error? You take the real, the predicted, take the difference of them, square them, and then you're going to add them and so on, right? So if you see, I arrived at this, this becomes this thing called a loss, but this is actually a computational graph in PyTorch, which is linking operations and data, which are tensors, to arrive at things. So let me move to this cell here. So now we have, let's say, T is a tensor, and Z, just to keep it simple, is WX plus B. And those are tensors as well. See that? And then we take E, and that is the final one, which is Z minus T squared. So that all of that is a computational graph that we start to define. And things like the W's are things that we need to calculate basically, right? So they're related to whenever we're taking a step, right, in the learning process, these W's need to be learned. So how do we learn them? Basically, there's going to be a W, which is W equal W plus a delta, which is the learning rate, LR, times this value associated with that weight. That should be a time. Yeah. So I'm going to call this W dot graph, for instance. All right. So basically, that's going to be the information that we're still missing. All right. So so you can see the losses come from these functions. These functions are just tying together the real and the predicted, which are tensors and operations. And in there, we have this thing, the weights, which is the thing that we're trying to change, right? And so we have a computational graph that takes input data and goes in a forward step. At the end is this. You can think of it as a node called E that is basically Z minus T squared, right? So this E then is like at the ending point, and from there we can start doing a step called loss dot backward. And literally what loss dot backward is going to do is that for certain tensors in the graph that are identified as requires grad, it's going to basically calculate a derivative of this whole function in terms of that term. Okay, and that comes from calculus. We don't actually have to do that. All of that is in here, basically. And that's what we're going to look at right now, how that works. So if you took calculus, for instance, I'm pretty sure you had a function and then you did by hand the derivative of it, and that's kind of your intuition. But here it's a little bit different where you have the values, and then almost like those values go through a function that is the derivative, and you see the result of it. Okay? That's what you end up seeing. But that value that you calculate plugs in here, okay? And it'll determine, let's say, if you add or subtract the learning rate from the weight, and that determines how quickly or how slowly the weight is modifying. Does that make sense, guys? So that's where I'm not going to spend too much time on that, but we are going to do a Jupyter notebook just to kind of illustrate this as an exercise, okay? Any questions before we begin? All right, so let's take a look at this one. All right, so I'm going to start a new Jupyter notebook. And as I said, all of these are on the GitHub. You can get them from there. So I'm going to call this one AutoDiff, okay, for the differentiation engine in PyTorch. Torch. Okay. All right, so I'm going to start. I'm going to go to my my GitHub under traditional ML. And we've done these two. Now we're going to do, yeah, this one. Scratch gradients losses, torch NN. So as you can see, all that this is really like some examples of, I have like 3 examples, I think, of how this works. But notice that in the end, I'm tying it to how I started the conversation with E equals C minus T squared. And that is MSE, basically, one of the losses that you understand. Okay, so I'm going to create just some functions in Torch, some tensors. You're going to see something called requires grad, and we're just going to take a look at how that would work. All right, so once again, I'm going to import some libraries. Okay, so import Torch, NumPy, and Matplotlib. All right. So then I'm going to create a tensor. Okay, so Torch tensor 14.5. So there you go, a simple tensor. This one does not have the setting requires grad. So even if I put it in a function and I did loss dot backward at some point, which is equivalent to that E that I was mentioning, it would not be included as something that is updatable. All right, so something like NN linear will have that by default for the parameters inside. So now what I'm doing here is I'm creating a function. Notice it's a simple function. Y equal X plus 5, right? So I'm going to take that X, which is 14.5, add 5 to it, and it's 19.5. This is the same thing as creating Y equal WX plus B and even the GPT, right? It's the exact same thing. All these functions, taking tensors and running them through the functions. Remember, as you start doing this, this actually starts to become a computational graph, basically. Okay, inside, like in the inner workings of Torch. All right, so we've created that. Then we're going to look at automatic gradients and what that means. And it's actually a simple concept. You take a function, whatever it is, you know the value that requires grad. So that means that you take that function, whatever it is normally, you take the derivative of that function, which all it means is you have a function, and then it ends up being another function from that. Once that is the derivative as the concept of it, and then you plug in the value in both functions, and it's different. But the information in the derived version is actually useful. It gives you this idea of like, and we'll see that. Let's just keep it simple for now, positive or negative. Do I add something to the weights or do I subtract? And that way you're intelligently optimizing the weights. Do you guys see that? So that's the whole goal. Instead of randomly optimizing the weights, you kind of intelligently optimize the weights. All right, so let's take a look at that. And I think the example is pretty straightforward. So, all right, run it. So automatic gradients. So notice now, I'm going to take a tensor, but I'm saying requires grad. So this will have an association grad parameter that I will know, okay, this parameter is the derivative of the function. If I have a function, calculate the derivative of it, now I plug it in, this is the value I get, and that tells me if it's positive or negative, and I can use that information. All right, so now notice it's a 3.5, requires grad. Okay, so now I'm going to create an equation here. Okay, so y equals x minus 1 times x minus 2 times x minus 3. And I'm going to run my x 3.5 through it. And then what is the value of it, right? So 1.875 on the normal function. So that would represent like the neural network. But some very intelligent people, Jeffrey Hinton, all those, discovered that this is a mechanism that they can use for providing information to train the neural networks. Okay, so now I create a function here just so I can plot it. Same thing, it's the same equation, but it's in a function form. Okay, so now I'm going to go here and plot my function. So what do I do basically? I'm creating x1, which is the points. I think, yeah, it goes from -1 to 6. That's the range that I want. And on the y-axis, I'm going to give these values, and it's going to tell me that f at every single point, right? Because it follows that curvy behavior. So let me actually break this up at the points. All right, so I did x1, and then I just converted it to a tensor. Why do I convert it to a torch tensor? Because I'm going to want to do differentiation, and torch does that, not NumPy, right? So print it out. My values, -1, 0, 1, 2, 3, 4, 5. So that's the x-axis. And then I'm going to do I run it through the function. So now I'll be able to see for this x1, those are the resulting values. So now I can go ahead and just plot it. And it should be there. So that's basically, so -1 to 5, and this is the curve. Do you guys see that? For x, what was x? X was 3.5, and it said that it was 1.875, right? So 3.5 to 1.87. So 3.5, it's like there. Almost 2. Do you guys see that? So it kind of shows you where it is. This is the actual function, which would represent like the normal neural network. But at this point, you want to know for a specific weight, how do you modify it? Do you see what I'm saying? And that kind of intuitively, you can say, okay, you look at this and it's like a valley. Should you go down or up, right? So if your goal is that the lower you get, the lower that loss, in a sense, if I'm here at this point, then I would, kind of think, okay, I'm going to go up or I'm going to go down like in a mountain range. That's usually the analogy that you hear with these kinds of problems. Does that make sense, guys? That's the intuition. So then it comes down to answering the question, do I go up or down? Right, guys? So you're here in the normal space. So in the differentiation space, do you go up or down, basically? That's going to be the idea. So that's what happens with differentiation. It gives you that information. So we calculate now the gradient. Oops, no. Okay. So now I'm going to do that, and then you'll see that loss dot backward that we've been using, and basically what it does. So again, I'm going to create my torch tensor, and I'm going to set requires grad to true. Okay, 3.5. That's what the value is, right? Same function over here. Just I'm not going to plot it anymore, right? That's my y. 1.875. That's no mystery, right? You've seen that. But now, check this part out. So y dot backwards. This is the thing that you guys have seen, but we just use it for loss. Why do we use it for loss? It's because y minus real, right? So the y minus real squared or whatever it is becomes loss. Here, this would just become y or or e. And so in this case now we have x, we have the function, and we're basically doing y dot backward, which is basically taking the derivative of this function. So imagine in your imagination that there's going to be a second function now. And when you plug in the value into that second function, it gives you another value. And that's the value that you're going to use to update the weights for that particular weight. So now notice I did y backward, just like we always do in PyTorch. The next step would be, after dot backward, to do dot step, if you remember in the training loop. So here I don't have that because I'm not really updating the weights. I'm just showing the derivative equivalent of it. So now I'm going to go ahead, and here it is. The derivative of y is this one. 3x squared minus 12x plus 11. So this function, this one over here, x minus 1 times x minus 2 times x minus 3 is the original. And if you analytically by hand calculate the derivative, you would get 3x2 minus 12x plus 11. So now the key thing, and I leave that, as a fun exercise, figure out by hand, go from here to here, and you'll see that that's what you get. More importantly, though, when you plug in the value, it'll match whatever we have in our x dot grad. So what I mean by that is, notice I'm going to grab x dot grad, right? So x is 3.5, right? X, the original one. But when I do x dot grad, it is not the same number. Look, this is 3.5. This is 5.7. Why? Because that value is the value, but going through the other function, right? So going through, or sorry, not 1.87, but it is 5.75. So if we go over here, I'll take this, right? So notice that this here is exactly this equation here, the derivative of the original one, right? Because 3x squared, right? So it's 3 times x squared, so 3.5, minus 12 times x, 3.5, plus 11. Do you guys see that? So initially, we took 3.5 x, we ran it through this one, and it gave us 1.875. That's like the normal neural network function, right? But we know this is just how it works. Like this is like gravity exists and it is whatever at 9.8. This is how it is. So we use the derivative as a concept, take this equation, do the derivative of it, which gives you this idea of like the slope of the curve. And so this equation becomes this one over here. Got it? So from here to here. But PyTorch doesn't actually give you this equation. Like PyTorch does not care about that equation. What it does care about is once you plug in x, what is the result, right? So when I take x, which is 3.5, run it through the function, I get 187. When I do the same with 3.5, but on the derivative of it, I get 5.75. And you should be convinced that when I plug it in, I also get 5.75. So it's correct. Yes, do you have a question? Should be what? Which degree? 3. It's I checked this before the class today. It's correct, yeah. Like I double checked it. I knew people would ask me.
It's the derivative.
Yeah. Go ahead and do it. I'm 100% sure it's correct. I double checked it, but so you'd have to this. Hopefully, I don't have to do this, but this is like you have to do. You have to like figure this one out and derive it. So it's like x times x is x squared, and x times minus 2 is minus 2x, minus 1 times x is minus 1x, and this minus 1 plus 2, and then arrange if you have to, and then do the same for this one. Rearrange. That will give you an x cubed thing, as you say, and then that thing is what you derive. Do you see what I'm saying? Yeah. So this is actually the derivative of it, of this one. But I didn't put it in the terms like you're expecting this to be x3, right? And something like that. So if we wanted to like work it out, I mean, it would be x3. I think this is 3 times, 4 times 3 maybe, or no, this was x squared.
Yeah.
So x squared times 6, right? So this was, and then this was probably x. And maybe a constant of some value. Got it? Good one. But I recommend, no doubt about it, take this one, do that operation, arrive at the function that starts with to the x3, and then take the derivative of it, and you should get this guy over here. Okay? What's important though, with this example is that I'm showing what, this is the neural network thing, right? And then if we plug in the value into the function, we get 1.87. Once that backward takes effect, it's equivalent to having this equation. And then when you plug in the value there, you get 575. That's your x grad. And notice it's the same as over here. So, and that's the value that you use in the optimization of your weights for that particular set of weights. Questions? All right, great. So that's kind of one of the concepts I wanted to do today. Go over this idea of derivatives. This is a slightly more complex example, but it should be the same. And I guess we have a little bit of time, so let's do this one. And it should be the exact same idea, right? So this one has just more complexity. All right, so this one is y equal x2, and then z is equal to, if you look at it bigger, right? Z is equal to 2y plus 3, where y depends on x2. An analogy to this would be hidden 1 becomes the input to hidden 2, hidden 2 becomes the input to hidden 3, and so on in the neural network. Do you see that? But at the end of the day, you guys are constructing a graph. Okay, so now what do? You have to do something called the chain rule, where basically you want to get the derivative of z in terms of the original x, but there's like a whole bunch of steps in between. So then what you end up doing is the derivative of z in terms of y times the derivative of y in terms of x. And this is that famous chain rule thing that you hear about all the time, okay? At the end of the day, this comes out to be the derivative of c in terms of x becomes 4x. Okay, so that's what we're going to test right now. Again, as an exercise, go ahead and do this analytically. But you can see here, we're going to take the same example. Now imagine if this looks complicated, think about ChatGPT or Llama and how massive those networks are. All right, so I'm going to say, I think we have enough time for this. So I'm going to say another example. Another example. Okay. I'm going to, right, so I have a tensor once again, x 3.5 requires grad because really these x's are going to be weights, right? That's the thing that I need to update. So I'm going to hit that 3.5 does require grad. That it's like an amazing solution, right? So somebody very clever just said, hey, let's just mark the things that we want to know the derivative for, and that way we can update them. Okay. So I'm doing this one here. So now I have my function. If you look over here, this one's a little bit more complex. So I'm going to go here, and you can see this one. Y equal x times x. Well, that's just x squared, what I have in my here, right? So it's x squared. And then this one is z equal 2 times y plus 3. So that should be this one, 2y plus 3. But remember, the whole point is that we're connecting c to y and y to x. And that's all things that we want to, we want to figure out that x basically, because that's the thing that we say requires grad. So again, what are we going to do? Let's go back to the code. Let's run it. Okay, so I have my my functions there. So now, quite simple, I invoke z and I say backward. But because I marked that x requires grad, I will have that grad component, which is equivalent to I take that input, goes through the function, or that input goes through the derivative of that function. And then I use that result to update the weights. Okay, so I'm going to go ahead and do that. Done. See how, like magic. All right, so now that it's done, I can proceed to do the same exercise, x dot grad. Okay. 14. That's the actionable information to update the weights. So let's, I know that 4x is the derivative of that original function. So I did that here. So you can see the derivative of c in terms of x with the chain rule is dc over dy times dy over dx. And dc of dx was this. And then dc over x, the simplification of it is 4x basically. So the derivative of this guy is this guy, so 4x. So the result of the grad is 14. So now the input is so here 14. So 3.5 times 4. Yeah, 14, right? 3, yeah. And that's it. So you can see this is like the analytical solution of the original function. The derivative of it gives you 14. But if you just do the grad of it with after backward, you also get 14. So in essence, in PyTorch, we don't much care about 4x, or we don't much care. We'll never see the result of these derivatives, but we do see the value that results. And that is actually what will be used to update the weight space. Hopefully that made sense, guys. So that's, I did this example. Play with these, do them analytically. That's my suggestion for you guys. Next Thursday, I will do another example. It's slightly a little bit more complex. I mean, it's kind of the same. And then we'll tie it back to that E. And then I still have one more Jupyter. And then finally, we'll move on to one of the other further algorithms in deep learning. Currently, remember, you have one homework assignment due, I think, tonight. And then you have, right, it's due tonight? When is it due?
Are you talking about the very first?
Yeah, the cyber data set. Oh, that was due. Okay, great. You guys all submitted, correct? All right, perfect. So I'll start grading that. And then you have a new homework assigned to you, which is to pre-train a GPT while web scraping the veterinary websites. Okay, and I showed you a GPU today, so you can also use that. All right. Sir, I'll make a note of it right now. Thank you. All right, guys, we'll stop here for today. I'll stay for a few minutes if you have questions. Otherwise, we are done. Good night. Sign in sheet. Thank you. Sir.
Just to confirm,
Yeah.
in the beginning, when you showed the assignment, like which will be like which will open today, right? Like it says like
Yeah.
few numbered code, but it also says available.
Give me a. Oh, this thing is still recording.